Okay, just to get started with the announcements, remember that we don't have class on Monday because it's a holiday. So this is going to be our last class meeting before the assignment is due on Wednesday. So the assignment will no longer be visible on Blackboard after 11 a.m. So you have to submit it before you come to class on Wednesday. And just as a reminder from what I'd mentioned at the first class meeting, that it needs to be submitted as a PDF file, a single continuous PDF file, meaning that all of the pages are combined in a single file. Any questions about that? We're going to go through a couple of examples today that may further assist you in being able to do that assignment. This is still some information that's coming out of Chapter 7 of the textbook. So hopefully you've received that by now, or at least maybe it's coming soon. We had to kind of move quickly through the shear velocity slide in class on Wednesday, and so I wanted to reiterate some of the points that are on that. A fundamental equation is one that is grounded in the basics of physics, and an empirical equation is one that is made up from observation and curve fitting. So this equation on the left describes the head loss due to pipe friction in a fundamental way, where we're looking at the first principles of shear stress, the length over which shear stress is applied, the geometry of the pipe, meaning the hydraulic radius and the unit weight of the fluid. And so this is like the real way to measure head loss due to pipe friction, but we're not able to use this equation very often because it's not convenient for us to directly measure shear stress. And so what we instead do most often is we use an empirical estimation technique for determining how much head loss is due to pipe friction. And that's based on some parameters that we can measure directly, like the velocity of the flow, the length of the pipe segment in question, the diameter of the pipe. And then there's some friction factor, which has been derived from lots of observations. Over years and years, scientists have looked at different pipe diameters and materials and flow conditions and have tried to come up with different techniques to estimate that friction factor. So if we combine these two things together, if we say, on the one hand, we know the real way to measure head loss due to pipe friction is based on shear stress, and on the other, the way that we're usually going to do it is an estimation technique based on a friction factor. Make those two equal to each other, and then just cancel out like terms and simplify. This is what we end up with. And so what this does is it allows us to relate pipe friction factor to shear stress. Now, this idea of shear velocity is just a recognition that on the left-hand side of this equation we had the shear stress divided by the density of the fluid. So those are both, density of the fluid is a property that depends on temperature, and we can know that with some pretty absolute terms. And shear stress can be either estimated or we can be working on a problem where that's a given. But we've got this ratio where if we take a look at the units, shear stress is newtons per meter squared. Unit weight is kilograms per cubic meter, so the reverse of that since it's in the denominator. And then further expand out, a newton, for example, is a kilogram meter per second squared. And cancel things out, and lo and behold, what we have after like terms cancel is meter squared per second squared. And so the square root of that then would give you units of meters per second. And so shear velocity then is just the variable that we assign to the square root of the shear stress divided by the density. It has units of meters per second, and it's a way for us to express how much shear stress a liquid is applying to the boundary that it flows next to. So you have a problem or two, I think, on the homework assignment that asks you to use this expression where you're relating the shear stress, the velocity that's measured or given, and then the friction factor. So it's just a way for us to kind of tie together the reality and the estimation side of energy loss due to pipe friction. Now, we've talked about circular conduits so far, but shear stress can also apply to open channels. And so this is a trapezoidal channel, which is a geometry that's pretty common in engineered channels because it's easier to construct than a rectangular channel. And rectangular channels can only be supported with either rock or concrete. And we could have a trapezoidal channel like this with a grass-lined surface, or if it was asphalt paved or so on. So it's just convenient in terms of construction and maintenance. The variables you can see here, the bottom width of a trapezoidal channel, we assign a lowercase b. The top width, depending on where you're getting your equations from. Some books call that T with a capital T. Some books, ours, use capital B for the top width. Y is the depth of flow. And then we define the slope of the sides of a trapezoidal channel by how many units of horizontal there are for 1 unit of vertical. And so you can see here that the side slopes here, it's a ratio of vertical to horizontal. And we just say let T be whatever distance there is in the horizontal that's coinciding with 1 unit of height. And so if you know T, then you would be able to determine the length of this segment given the depth Y. So the formula you've seen before for how to determine shear stress when you know the fluid's unit weight, the hydraulic radius that the flow is going through, and S sub F. Does anybody know what we named that variable? Do you remember? There's a couple of different slopes. S naught is the channel slope. S sub F is which slope? Very good. That's right. It's the energy grade line, slope of the EGL. So this equation applies to open channels as well as it does to enclosed channels, but we had kind of a simplification we used when we had closed conduit flow. I told you that the hydraulic radius could be diameter divided by 4 if it's a circular pipe that's flowing full. That's not the case for a trapezoidal channel. For one thing, we don't have diameter here. It's not circular. And then the other thing is the wetted perimeter does not include the top because the water is in contact with air. So wetted perimeter is where does water touch the channel, or where does water touch something that isn't moving. So in this case, if this was a concrete lined trapezoidal channel, water would be touching this side segment and the bottom and the other side segment, but there isn't resistance being applied to the fluid by the air at the top. Maybe a little bit of resistance, but nothing like what it's encountering in the channel itself. So I just wanted to show you an illustration of how we handle the trapezoidal geometry. We'll spend a lot of time on trapezoidal geometry later in the semester, but it does kind of come into play when we're just talking about resistance to flow. And the energy grade line is defined for an open channel segment as the energy loss due to pipe friction, or not pipe friction, but the energy loss due to resistance at the bottom of the channel and the sides of the channel divided by the length of the segment that it's acting over. So here's the example that I just wanted to introduce so that we get a first taste of trapezoidal geometry. So what is the hydraulic radius, this is asking, for a trapezoidal channel in terms of the bottom width, the depth of flow, and the side slope, T. So hydraulic radius is defined as the area divided by the wetted perimeter. And so the area of a trapezoid like this, if you think about, there's maybe a couple of different ways for us to consider the area of a trapezoid. That's poorly drawn, but you'll get the idea, I hope. So there's a rectangle and 2 triangles, which if we put them together, that's another rectangle. So what you could do is just calculate the area of this segment, which is the depth times the width, plus the area of the 2 triangles on either side, which would be the top width multiplied by the depth, and then that gives you the area. Another way to do it is that, let me redraw it with a little bit more. Okay, that's not quite so bad. We've got B the bottom width, and then this is the depth of flow Y, and then we're defining this 1 to T is the side slopes. So area can be expressed as B times Y plus Y times T times Y. So this, the side triangles, Y is the height, and then this segment on the top, that is T times Y. So the length of that, this is basically the same thing that I just showed you. B times Y is the center rectangle, and then Y times T times Y is the two side triangles added together. The wetted perimeter is B plus 2 times the square root of Y squared plus T times Y squared. And one thing I'll point out is that this length is the square root of Y squared plus TY squared. Because it's, you know, the height is Y, the top length is TY, and so we can find the length of this segment by just finding the square root of the sum of the squares. And there's two of them because there's one on the left, one on the right. So we can further simplify this. The top is B times Y plus Y times T times Y, and then divided by B plus 2Y square root of 1 plus T squared. So we're just factoring out the Y term from underneath the square root. And so this is the hydraulic radius then for a trapezoidal channel. And that's just kind of scratching the surface of the fun that we'll have with trapezoidal geometry. The trickiest thing comes when we're trying to determine what the flow depth is. So about halfway through the semester, we'll revisit this, and we'll be combining together trapezoidal geometry with some empirical equations that allow us to determine flow depth when we know the volumetric flow rate Q. Any questions about trapezoidal geometry? All right. So these empirical equations that estimate the relationship between energy loss and flow conditions have been around for a long time. One of the earliest such equations was the Chezy equation, and it's not used much anymore. So you probably won't do a design that's based on the Chezy equation, but you may come across things that have been built that were built using the Chezy equation for their calculations. So, you know, we've got a lot of infrastructure out there that's 100 years old, 120 years old, even older. I was in Wheeling last weekend, and there's a bridge there that's, I think, more than 150 years old, and it still looks pretty good considering. So there's stuff out there that was designed using the Chezy equation, so I think it's important for you to understand what the mindset was there, like what it was trying to relate. What the Chezy equation says is that if you know the slope of the energy grade line, S sub F, and you know the hydraulic radius of a channel, there's some proportionality factor, C, to what the velocity of flow will be. So for example, if we had water flowing through a pipe and it was a pretty smooth pipe material, so a low Chezy coefficient would be something that has a high C value. So there are different units depending on whether you're working in British gravitational system or SI. So very smooth and SI units would maybe be as high as 77. So if you have a really smooth pipe, then they'd put this C value as 77, and you'd know the slope of the energy grade line, which is basically how much energy is pushing the water through the pipe. You know, it could be energy that's added to a system by a pump or an elevated tank, but if you know the elevation difference between the inlet and the outlet, you could use that to determine the slope of the energy grade line. Or you could calculate the slope of the energy grade line by some difference in pressure between 2 points. But the energy grade line is like the driving force that's causing water to move through the conduit. So if you know that energy grade line, then you could determine what the velocity of flow would be. So, I mean, it was good for what it did, and while it lasted, somebody named Manning came through a few years later and improved on the Chezy equation by observing that it wasn't necessarily to the 1/2 power that caused the best fit, but he determined some modified roughness coefficients and estimated that it was to the 2/3 power that maybe caused a better fit. So you probably won't see the Chezy equation, but it just maybe gives you a glimpse of this idea of empirical equations and a way to estimate the relationship between the driving force that's available to push liquid through a conduit and then the resulting velocity. So if you wanted to use the Chezy equation to calculate flow rate, Q, you just determine the flow velocity, V, and then multiply it by the cross-sectional area of the pipe that the liquid is flowing through. In our book, they relate the Chezy equation to the friction factor F that is applied in the Darcy-Weisbach equation. So I wanted to point out that formula. I think maybe there's a homework problem that asks you to relate Chezy equation or friction factor. I can't think of why I would have pointed it out otherwise, but it's there. Okay, so velocity distributions describe the fact that there isn't just one velocity in a pipe. There is a variety of different velocities in a pipe depending on how close you are to the edge of the pipe. And we talked about this a little bit on Wednesday, how when you are really close to the edge of a boundary that's not moving, whether it's a river bank or whether it's the wall of a pipe, that the liquid velocity is 0 in the immediate vicinity of that stationary object. The water can't slip frictionlessly over a stationary object, but the further away you get from those surfaces that are imparting resistance to flow, the velocity will be increasing. So this represents a circular pipe. And what this is showing is that if we have laminar flow conditions, meaning that conditions are really slow moving, you know, the Reynolds number less than 2,000 means you're going to have very low velocities. For very low velocities, there isn't turbulence in the flow that would cause a disruption or interaction between layers. And so what happens is a parabolic velocity distribution will dominate in laminar flow conditions. And so at the edge of the pipe, the velocity will be 0. At the center of the pipe, where you're the furthest away from the pipe wall, that's where the velocity would be the highest. When you have turbulent flow conditions, the velocity distribution is no longer going to be parabolic. When there's a lot of random interaction between fluid particles and the edge wall, the distribution can be described as more logarithmic. And even among the logarithmic, it may be that at one part of the pipe, at one moment the velocity is a little lower, then it's a little higher. There was a slide that I showed you on the first day that kind of illustrates this point that there's a lot of random variation inside of a pipe. So this is showing that at the center of the pipe, the water is flowing more freely, that it's less under the influence of the side turbulence. And so the average velocity distribution is more flat in the vicinity of the pipe. Is more flat as you get into higher flow velocities. A boundary layer is a surface that is stationary, let's just say that we had a lot of water that was flowing to the side. We had so much of it, really a big depth of fluid that was flowing sideways, that it's outside of the influence of whatever is containing the flow. And if we introduced a plate, like if we just dropped a metal plate parallel to the direction of flow, then that plate would cause a frictional resistance to the liquid that's in the vicinity of the flow. So here, prior to the fluid encountering that stationary plate, you see that the velocity distribution is even, that as you go up vertically or down vertically, there's no variation in flow. But when the liquid encounters this plate, the fluid that's right next to the plate is moving much more slowly, and here is a velocity distribution where the velocity is 0 at the surface itself, and as you get further away, the velocity is increasing as you get further from that stationary surface. So at the surface itself, it's not slipping because a shear stress is applied by the plate to the fluid, and the velocity is decreased in the vicinity of the plate, such that we may have laminar conditions. So here, prior to the flow encountering the plate, it could have been that the velocity was high enough that we had turbulent conditions, but there's going to be a boundary in which the velocity is low enough that even though bulk flow is turbulent, there's a thin layer of laminar flow in the vicinity of the stationary surface. So an equilibrium is established once the water encounters the plate and it's like no longer slowing down. You can see that the slope that was increasing for a little while tapers off, and now it's just parallel to the plate itself. And so what this is kind of conceptually illustrating is some region where the velocity is below the bulk flow velocity and may be as low as laminar conditions. How thick this boundary layer is depends on things like the viscosity of the fluid, the characteristics of the plate itself, whether it's smooth or rough, and that's going to have an influence on how deep into the flow the boundary layer extends. If the velocity upstream increases, what that's going to do is it's going to suppress the thickness of the boundary layer. And if the velocity, the bulk velocity decreases, then that would increase the thickness of the boundary layer. So the region in which conditions are laminar it's going to be a larger region if the overall velocity to begin with was lower. All right, this figure comes from our book, and the first time I encountered it, it took me a long time to wrap my mind around it. And I think chances are that probably, I'll do my best to explain it to you today, but most people in here probably aren't going to really understand this figure. It's something you have to look at a couple of times and keep thinking about, and then look at it again and think about it a little bit more, and then maybe it'll make sense. So I'll do my best to explain it, but if you're not quite there when we're done talking about it, that just means keep thinking about it. You know how sometimes they say if you fall asleep, sometimes it comes to you the next day? This figure may be one of those situations. But all right, so with all of that said, water's flowing through a pipe, and this is illustrating the thickness of the boundary layer. So we've already talked about what causes a boundary layer. It's just that the velocity has slowed down in the vicinity of a stationary material. So this is a hollow pipe that fluids are going through, and at the edge of the pipe, the water velocity is 0, and the shear stress is high. So that's what this is showing in the x direction, is the intensity of the shear stress. So this would be 0 shear stress on the figure, and this is the shear stress at the edge of the pipe boundary, so maximum shear stress here. And as you get further away from the edge of the pipe and closer to the center of the pipe, this is showing that the shear stress is decreasing. So let's say that we had turbulent flow conditions, that the water velocity is going through here pretty fast, such that in bulk, conditions are turbulent, that's this curve. So shear stress in turbulent conditions, it's showing the thickness of the boundary layer, and it's also showing the distribution of shear stress as you get further away from the center of the pipe. In laminar conditions, when conditions are laminar, that means a slow-moving velocity, and this is just showing that the shear stress doesn't extend as far into the liquid when you've got laminar conditions, that the pipe isn't holding on to the flow as deeply into the pipe. It's just at the edge, maybe, that the pipe is extending its influence over the fluid. So a boundary layer, or sometimes we can think of the laminar sublayer as being the one that's important to us, because the reason why we're talking about boundary thickness is there's different equations and different conditions that apply depending on whether the boundary layer is really thick or if the boundary layer is thin. And more specifically, we're interested in what's the size of the boundary layer compared to the thickness of the roughness elements in the pipe. Because some pipes are smooth, some pipes are rough, so we want to know, how does the thickness of the boundary layer compare to how rough the pipe is? So that's why we're thinking about it. So this is saying that the boundary layer thickness depends on the flow conditions and how rough the boundary itself is. So if you have a fast velocity of flow through the pipe, then that's going to be corresponding to a high shear stress, but the boundary layer, in which conditions are laminar, will be small. So the shear stress extends far into the fluid in high velocity, but the thickness of the boundary layer will be small. And then the flip side of that is in slow velocity, which is going to tend towards laminar conditions and a low shear stress. Then that's going to have the shear stress doesn't extend as far into the fluid, but the laminar boundary layer is bigger. So directionally, that's the concept between boundary layer thickness, shear stress, and fluid velocities. Okay, so maybe that does make sense. I don't know. Maybe I was overselling it. But do look back on this figure, and it's something that I would like you to be able to describe what's going on in this figure. So know it well enough that you could explain it to somebody else. The equivalent roughness, sometimes called the equivalent sand roughness, is a means of expressing the equivalent diameter of a sand grain that would be required to cause the same resistance to flow under turbulent conditions. And we can measure the equivalent roughness in SI units or in traditional units. And so here's some materials that pipes have been made of through the years. Some of these are still commonly used today. Like it's common to have pipe made out of galvanized or cast iron. There are concrete pipes. There are not as many wood pipes today as there used to be. It's hard to believe that in the same way that they used to carry like water in barrels, they used to make pipes out of wood in some places where that was the most convenient material available to them. So if this diagram, I think, does a good job of explaining what we mean by sand grain roughness. Pipes actually have a random distribution in roughness. And to allow us to compare dissimilar pipe materials, what they did was they said, well, let's express the random roughness in terms of what sort of a standard roughness height would cause a certain amount of friction. So that's the equivalent sand roughness idea. And you'll use this a lot when you calculate the friction factor not using the Moody diagram. Well, even if you do use the Moody diagram, you have to use this, but we're not going to do much with the Moody diagram aside from a couple of homework problems, because in design it's not convenient to always look at some goofy figure if we could instead just have the machine calculate a friction factor for us. There are equations that allow us to estimate the friction factor without us needing to, get really precise on where on a curve something is. And so we'll talk about the Jane equation and the Colebrook equation next week. And in those, the material type is one of the inputs that tells us what the friction factor is. Oh, here's a picture that I've covered up. That is a, wanted you to see this wood pipe. I used to make wood pipes similar to a barrel. You can see that there's a metal ring around it, and then just that the wood segments are joined together. Very labor intensive to do that. There are a couple of equations and techniques that have been developed to estimate the thickness of the boundary layer, and Morris and Wiggert suggested that if we knew the shear velocity of the fluid and the fluid's kinematic viscosity, that you could calculate the boundary layer thickness this way. So they empirically observed the thickness of the boundary layer relating those two terms. And remember, shear velocity depends on the shear stress and the fluid's density. And according to the Morris and Wiggert criteria, if you calculate and find that it's greater than 1.7 times the equivalent sand grain roughness, then the laminar layer dominates, meaning that we have hydraulically smooth conditions. So what that means is that the thickness of the boundary layer is much, much higher than the thickness of those roughness elements. So it's more than 1.7 times larger, so it's fully submerging those little roughness bits in the pipe. So whether it's like steel grain or concrete, if you think about, you know concrete's rough, you probably run your finger over finished concrete and you kind of still feel the sand that's in there or the imperfections in the surface. So if the boundary layer is much larger and fully submerging those, we consider these hydraulically smooth conditions, and it's hydraulically rough if the boundary layer is less than 0.08 times the thickness. So those are two pretty extreme, like there's a lot of middle ground that either isn't hydraulically smooth or isn't hydraulically rough. It's in the middle where both, what we'll find is the relative roughness and the Reynolds number both play a role in determining the friction factor. When we're at these extremes though, only one or the other will determine what is the friction factor. We'll only have to look at the influence of the relative roughness or the influence of the flow conditions at these extremes when either the roughness elements is projecting well outside of the thickness of the boundary layer and it's hydraulically rough, then it only depends on the Reynolds number at that point. All right, so I got some confused looks when I was walking you through the homework problem, you know, those hints that I gave you on Wednesday for the problem 8, I think it is, on the homework. And so I thought it's probably going to be good for us to go through this example problem and get a little bit more practice applying the energy equation. At least, you know, the energy equation as it's expressed in our hydraulics book is being presented a little bit differently than you may have seen it in fluid mechanics, where the energy equation maybe was written in terms of, not in terms of length. So let me walk you through what we've got. This is very similar to homework problem 8. We've got an elevated tank and a building where we know what pressure we want to be present at the top of the building. Oh, in this case, it's actually saying the ground floor. So we want 350 kPa at the ground floor. And you can see that the ground floor of the building is 20 meters above some datum. So we want to know how high should the water surface in the tank be above that same datum, where we're going to assume that we have friction losses of 16.4 meters. So that's just a given. And the pipe is 200 meters long, 250 meters long and 250 millimeters in diameter. All right, so calculating the water surface elevation, we're going to have to start off by just applying the energy equation there. And so location 1 is at the interface of the water and the air, and location 2 is at the base of the building. So how do you know what to choose as location 1 and what to choose as location 2? You assign those where you know things, where you know a lot of things. And so we know a lot here at the base of the building. We know the pressure that is desired, and we know the elevation of the building there. And what we're going to assume, and it's a pretty good assumption in the energy equation, is that the velocity term is often negligible. So in the energy equation, P1 divided by gamma plus Z1 plus V1 squared divided by 2G, and not written here, though, is the H sub P term, the pump head term. There's no pump in this, so we'll omit writing that, is equal to P2 divided by gamma plus Z2 plus V2 squared divided by 2G plus head loss. Now, by the way, we've got H sub F and H naught. Those two together are the head loss. H sub F is the head loss due to pipe friction. H naught is energy loss due to local losses, like when water goes around a bend or through a valve. Those are local losses. Some books kind of pejoratively describe those as minor losses, and oftentimes the magnitude of local losses are smaller than friction losses, but not always. Sometimes you have more energy loss going through fittings than you do through pipes. So here, the formula as it's written here, it's just saying H sub L, and then this says neglect local losses. So that's saying H naught is 0 in this problem. Let's say that valves aren't accounting for any of the losses that are observed, that it's all the friction losses. Okay, so 1 is here at the top of the tank. 2 is at the base of the building. So what is the water pressure at that location at the interface of the air and the liquid?
Would it just be atmospheric pressure?
Just be atmospheric pressure. So now let's ask ourselves, are we going to work this problem in terms of absolute pressure or gauge pressure? Gauge pressure is we're saying, let's have the atmosphere be 0 as our starting scale. If we're measuring pressures in terms of absolute, then we'd use like 101 kilopascals as atmospheric pressure. Let's use gauge. That's what we'll typically do, is we'll just take for granted that, yes, atmospheric pressure exists, but all the pressures we're going to measure are over and above atmospheric pressure. So by that regards, we're just going to say that the pressure at 1 is 0. So P1 is 0. So we're going to cancel out that term. Z1 is the unknown. What must be the water surface elevation in the water storage tank? We're basically solving for Z1. That's what it wants us to know. Okay, V1. Now remember, the energy equation, location 1 means at a single point. It means at the tank. It's not talking about the velocity through the pipe. It just wants to know what's the velocity of the water in the tank. And we're going to do this idea that there's quite a bit of water in the tank, and even if it's not being replenished, which maybe it is being replenished, but even if it wasn't, the water level wouldn't be falling very quickly. And so we're able to neglect the velocity at location 1. The pressure at 2, so the base of the building, we know that the pressure at 2 should be 350 kilopascals. So Z1 is equal to 350 newtons per meter, kilonewtons per meter squared. And then the unit weight of water, we're not given any particular temperature. We'll just use the standard 9.81 kilonewtons per meter cubed. That's the unit weight of water in terms of kilonewtons per meter cubed. All right, plus Z2 is 20 meters. The velocity of the water flowing through the pipe we'll neglect. If we wanted to be super precise, then we could include the velocity through the pipe. And I guess, I don't know, let's go for it. Let's do that. Just to show you what I mean. We know that the flow through the pipe, it says in the problem statement, is 12,000 liters per minute. So 12,000 liters per minute, that's the same as 12 cubic meters per minute. And that's the same as 0.2 cubic meters per second. If we divide 12 by 60, so the flow rate is 0.2 cubic meters per second. And we know the diameter of the pipe is 250 millimeters. So area is pi d squared divided by 4. So pi times 0.25 meters squared divided by 4. The cross-sectional area of the pipe is 0.04909 square meters. So the fluid velocity is Q divided by A. If we want to know, like, what's the speed of the water on average traveling through the pipe, we have 0.2 cubic meters per second divided by 0.04909 meters squared. So the water is flowing through that conduit at a velocity of 4.074 meters per second. That's pretty fast. It's moving along through that pipe. All right, so now, I was going to suggest earlier that we neglect the velocity head at 2, but I'm glad we didn't, because 4 meters per second is a pretty significant speed, and so the velocity head may not be negligible after all. I'm going to erase this part where we determined the velocity. Hopefully you've got that copied into your notes, and maybe I ought to bring it up on screen just so that it's included on the video for the benefit of anybody who will be reviewing this later. All right, so what we've done so far is determine the velocity, of course. And we're going to apply it to the energy equation. So we already said we've got the pressure head term, the elevation term, and then the velocity term, v squared divided by 2g. So that's 4.074 meters per second squared divided by 2 times g. And then plus the head loss. So that's 16.4 meters of energy is lost due to pipe friction. So all of that allows us to calculate the elevation that's required for the tank. So the tank should be at an elevation of 72.92 meters, because the tank has to be high enough to overcome the elevation change to get to the building. 20 meters of that elevation is to get us to the base of the building. 35 meters of it provides the pressure head. You got the velocity head of 0.846 meters, and then the energy to overcome pipe friction is 16.4 meters. All right, so that answers part A. Part B, what is the Darcy-Weisbach friction factor? Okay, here's our formula for the friction factor, and we were given the head loss in this problem. Most of the time that won't be the case, but here we were. We knew the head loss, so we just rearranged the friction factor formula to solve for F. So if we rearrange that equation, it's H sub F times D times 2g divided by length times velocity squared. So 16.4 meters times 0.25 meters is the diameter of the pipe, times 2g times the length of the pipe, 250 meters, and the velocity, 4.074 meters per second. And we have to square that. So for this pipe, the friction factor is 0.0194. If we were to back calculate that based on the known head loss, the thickness of the boundary layer according to the Morrison-Wigert criteria, to determine that, we're going to have to know the slope of the energy grade line, because we're going to need to be able to calculate the shear stress. And so the shear stress requires the slope of the energy grade line. Luckily, we know both the H sub F and the L. So let me just refer to this in the PDF. Maybe that'll be easier than writing it on the bottom of the whiteboard. So we calculated the friction factor. So if we calculate the slope of the energy grade line, what we're doing is we're just saying if you lose 16.4 meters of energy over a length of 250 meters, then the slope of the energy grade line is 0.0656. And we can put that into the shear stress formula, because we know the unit weight of the water is 9810 newtons per meter cubed. The hydraulic radius is the diameter divided by 4, because this is a circular pipe that the water is going through. And so we now have the shear stress. And then finally, with the shear stress, we can calculate the shear velocity by dividing the shear stress by the density of water. The density of the water being 1,000 kilograms per cubic meter. Take the square root. So the shear velocity is 0.2 meters per second. And the Morrison-Wigert criteria says use this formula of 11.6 times the kinematic viscosity divided by the shear velocity. So it says that the thickness of the boundary layer is 5.8 times 10 to the minus fifth meters. So that's less than a millimeter is the thickness of the boundary layer. And that was the last thing, I think, here that we were looking to do. Calculate the thickness of the boundary layer, use the Reynolds number, the friction factor, and the relative roughness to determine the pipe material. Well, we won't go that far. It was just like we could infer what is the pipe material by looking at these different relative roughnesses, like basically finding on the Moody diagram what is the roughness, and then from the Moody diagram, if you know the roughness, then you can determine what the pipe material is. So that's all the time we have for today. It's 11:50, so remember that over the long weekend you should be working on the homework. I'll do my best to check email occasionally over the weekend if you have any questions, or you can call me on Teams and I'll be happy to pick up if I'm available. So I'll see you next Wednesday.